Okay. All right. So, good morning, kids. How y'all doing? All right. So we got Christmas trees and New York Yankees in the background and random things, and Hannah's in her car, it looks like. And love technology. Okay. So let's start off with this. Anybody have any specific questions you want me to go over on that assignment? You can either type it into the chat. Hold on. I got to monitor a whole bunch of different things right now, so bear with an old man. Number 8. Okay, all right. Let me get, I got to get one thing. Hold on. We're going to get there. Hold on, I just had, there it is. Okay. Hold on, I got to let in more people. No, we're all good. Okay, all right, so number 8. So here's the deal on number 8. So you've got the ride like this. Hold on. You got the ride like this, okay? And here's Bubba. So here's the main idea. So imagine that you're in this ride and this room is spinning around, okay? And you're like this. Now, do not tell me, do not tell me, do not tell me. Oh, you're being pushed up against the barrel wall. Wrong answer. Remember, your body just continuously wants to go in a straight line. So if you look from like on the top of the ride, you know, looking down like this. So this is like looking down on the top, and here's the top of your head. Remember, you just want to move in a straight line. So all that's happening is this barrel wall is keeping you from going in a straight line. So the source of your centripetal force is the barrel wall, because as soon as if you could remove that barrel wall, snap your fingers, and that barrel wall would disappear, you would now turn into a projectile. So there's nothing inside of this ride emanating this magical force that's pushing you against it. Your body just wants to move in a straight line. So from the side profile of this deal, okay, so now this is like the side profile. So you're like this, okay, and because you're like this, your body wants to slide down. So what's happening is that there's that your body wants to move in a straight line, but there's friction between you and the surface that's keeping you from sliding down. So here's the main idea, is that when you have that barrel wall, so you have gravity pulling you down, so the frictional force has to be acting up, and then you have your centripetal force acting inward. So if you look at mu equaling force friction over force normal, okay? By the way, can you all see this? Somebody talk to me. Can you guys see the screen? You're good? Okay, all right. So you know what the coefficient of friction is, okay? And so you've got that number, but here's the whole kicker to this, is that that frictional force in this situation has to equal your gravitational force acting down, right? So instead of force friction, we're going to set that equal to Fg. Now, your normal force, remember, that's what's acting at a right angle to the surface, okay? So that's what's acting inward like this. So that normal force is going to be your centripetal force. So then you go, okay, well, instead of Fg, I'm going to put mg, and then instead of my centripetal force, or instead of normal force, I'm going to put my centripetal force, which is mass times your centripetal acceleration. So what you get is mu equals mg over mac. Masses cancel out. You get mu equals g over AC. So you know what your centripetal, you know what mu is, and you know what g is, so find your centripetal acceleration. So if you do that, trust me, you get 65.3 meters per second squared. Oh, sorry about that. So that's your centripetal acceleration. So that's about 6.5 times gravity. So what that means is if you were in this ride, you would feel 6.5 times heavier than what you do right now, okay? Which would be really, really uncomfortable. You'd probably pass out, to be honest. Okay, so now, once you get that, what you're asked on number 8 is that, what radius should the ride have? Let's take them, okay? And here's the deal. The other thing about this problem is that you're making a half revolution per second. So what you have to decide is, when you have a half a revolution per second, is that period or is that frequency? Okay, that's the million-dollar question. Is that because of the fact that it's revolutions per second, that's going to be the frequency. Okay, so if you're going to try and find the radius, you know that centripetal acceleration is 4 pi squared r over t squared. So you know what your centripetal acceleration is. That's that 65.3. So now you have this number. But here's the kicker. Because this is revolutions per second, that's frequency. So you need to take the inverse of that. Okay? Because remember, period and frequency are inversely related. So if you flip that over, that becomes 2 seconds per revolution. Now you have your value of t. Then you can solve for r. So if all goes well on number 8, you should get a radius on number 8 somewhere between 5 and 8 meters. Okay, so that's where that radius should end up on number 8, somewhere in there. Okay, Maddie wants number 9. Okay, so on number 9, here's what you got going. And this is very relevant to Kansas since we have a lot of wind turbines. So here's this wind turbine, right? And this thing is going to be spinning around. So obviously, if you're going to design this machine, you've got to keep this big, massive wind turbine from turning into a projectile. So you got to figure out, okay, how much centripetal force has to be exerted on this wind turbine to keep this thing from flying off? That's kind of an important thing because, you know, if you guess wrong, guess what? You've just ruined an entire high-dollar machine, and it's like, oh, I guess I did that calculation wrong. Ooh, that's a problem. Okay, so if you look on what's going to happen, first off, you got to start with this idea that you have 22.0 revolutions per minute. So right away, when you see revolutions per minute, this is what we just talked about. That revolutions per minute is your frequency. Okay? So the first thing that you need to do is say, okay, if that's revolutions per minute, I need to find the period, which is going to be the inverse of this. Now, but what you need to do is that's revolutions per 60 seconds, okay? That's your frequency. So then you need to take the inverse of that. So once you take the inverse of that, you get, I'll just save you some math, you get 2.73 seconds per revolution. So what that means is if you were watching this wind turbine and that wind turbine was here at the bottom, it would take 2.73 seconds for that thing to go all the way around and get back to this point. Okay, so that's what you're telling us, taking 2.73 seconds per revolution. So then you've got, they're 38 meters long. But here's what you have to watch, is that when you're going to do this, you need to figure out, first off, what's the speed in meters per second at the very end of this. So you just need to go v equals 2 pi r over t. So you're trying to figure out if you had, like, imagine that you have like a radar gun, and it's shot, and you're going to shoot that thing at the end of this tip. As this thing comes around, you want to know what's that reading going to be. Now, obviously the reading out here on the end is going to be much greater than the reading very close to it, because the outside edge is moving really, really fast relative to that inside edge. So with that one, if you do that right, you're going to get a velocity on number 9 around 90 meters per second. So on 9A, that's about 90 meters per second. And that's pretty fast, okay? Because if you consider that like the speed of sound is like 330 meters per second, if you are driving your car at like 70 miles per hour, that's about 30 meters per second. So the end of that tip is you know, that's pretty fast. But keep in mind, this thing is like 38 meters long, so that's about roughly half the length of a football field. So this is like this big, massive blade that's spinning. So way out there on the end, you're going to be going really, really fast. Okay? Then, on B, they want to know the blade is modeled as a point mass at the midpoint of the blade, how much centripetal force is needed. So let's talk about this concept of point mass. So we're going to use this concept of point mass when we talk about like gravitational fields. So what's going to happen here is that imagine that we're going to take that entire blade and we're going to act like all of that mass is located at 19 meters. Okay? So even though this whole thing is 38 meters, we're going to say like on average that all of that mass is concentrated right there. So, you know, you're going to have half of it that's going to be further out. You're going to have half of it that's going to be closer. But on average, we're going to say that that point mass is right here at 19 meters. So that's what we're going to say, okay, this is where this thing is located. So then, once you get that, then it's just a matter of going, oh, okay, well, your centripetal force, there's a couple of things you could do. You could do mass 4 pi squared r over t squared. You could go, that would probably be the easiest. Now, here's what you can't do, okay? This is what you have to be careful of. What you cannot do is go mass v squared over r and use that answer from 9a as your velocity, okay? You cannot do that, and here's the reason why. Because that 90 meters per second is the velocity at the very end of the blade. So on 9b, you cannot do this and use the 90 meters per second that you found up there on part A. That's the one thing that you cannot do. So you could go up here and recalculate that velocity and then do mv squared over r. But what I would recommend if I were you all, I'd just go with this. You know the mass, use a radius of 19 meters, use that period that you just found, 2 something and some change. So if all goes well on B, you should get something times 10 to the 6th. So on 9B, that amount of centripetal force is 10 to the 6th. So that's a lot, okay? I mean, that's 10 to the 6 newtons, that's quite a bit. So anyway, any of the other ones you want me to go over at all, you can chime in, type it in text, whatever. Now, I haven't seen anything, but let me go over one thing that I want to make sure that you all get. Up there on number 1, when you're swinging this bucket around, okay, whatever it is. No, you're swinging this mass around. When you get to part B and it says, is the mass going fast enough to complete the loop? There's a couple of things you can do on part B. And I don't care how you do this, I'm just going to show you some options. So one thing that you could do is that you could calculate the minimum velocity using V equals the square root of GERT. So this gets you your minimum velocity. So if you calculate that minimum velocity and you're going faster than that, you're going to complete the loop. So that's one option. You could also calculate the total force at the top using force centripetal minus Fg. If you calculate this and this net force at the top is a positive number, you're going to complete the loop. So that's another option. Okay? The other thing that you could do is you could calculate your centripetal acceleration using v squared over r. And if you calculate this centripetal acceleration and that number is bigger than 9.8 meters per second squared, you're going to complete the loop. But here's what you cannot give as an answer on 9b. Here's what you cannot say. You can't just say, oh, well, the force is positive. If you just say the force is positive, I don't know which force you're talking about. I don't know if you're talking about the centripetal force. I don't know if you're talking about the net force. I don't know if you're talking about the gravitational force. Okay? I don't know which force you're talking about. So here's what you cannot give as an answer to 9b. You cannot just say, oh, it's positive. Okay, that's way, way too vague. On number 3, that's the only answer on this assignment that should be a negative number. Because on number 3, let me kind of paint that picture of what's happening on number 3. So here's this car going up over the hill, right? Okay. So as this car goes up over the hill, remember, because of inertia, it always wants to travel in a straight line. So since this thing is going to want to travel in a straight line, it's you in effect like way less, mainly because of the fact that this wants to go like this. So when you're finding that force at the top, because you're going up and over the hill, that just means that the reading on the scale is going to be a little bit less because you want to travel in a straight line. So, and that's cool. So if you're going up and over the hill, you can have a negative number on that total force at the top, but you can do that because you still have the earth here to support you. Now, if you were trying to drive this on an inside loop, like if you were trying to complete this loop, it would be an epic failure. You would fall because of the fact that there wouldn't be anything there to support you. On number 4, okay? So on number 4, let's talk about that. So you have force total equaling force centripetal minus Fg. So on number 4, basically here's the idea. When you're at the top of this loop, here's what you have to remember, is that this total force is what you are going to feel, okay? This is what you are going to experience, okay? That's going to be vital. This is what you are going to experience. And this is always going to be a multiple of Fg. So on that first one, you're going to have 0 Fg because you want to be in a state of weightlessness. You don't want to feel anything. So that's going to be Fc minus Fg. Move that Fg over here. Mg equals mv squared over r. Masses cancel out. V equals the square root of g. So on A, I don't want to make sure this is right because if this is wrong, everything else is going to be wrong. So this answer on number 4A should be about 16 meters per second. Okay, so that's how fast you'd be going. You have to be going to just complete the loop. So what we're saying on this is that when you're at the top of that loop, you need a certain amount of centripetal force. And this is the key concept that you have to get. You need a certain amount of centripetal force. And what we're saying is that gravity is providing just that right amount of force. So you're in this arc, okay, and you'll see this later on when we get into planetary motion. Basically, you are in orbit. For just a little bit, you would be in a state of orbit because gravity is providing just that amount of centripetal force. So what's going to happen then when you get to like 6 on B, you want to figure out how fast you have to be going to experience 1/4 their weight. So what's going to happen on 16B is you're going to have 1/4 Fg is going to equal force centripetal minus Fg. You're going to move this over, so you're going to have 5 force mg equals mv squared over r. Masses cancel out. you get V equals the square root of 5 fourths GER. So what's going to happen here is that you're going to get a bigger velocity than you did up here. Because now, here's the key concept. This centripetal force now has to be bigger than what gravity is going to provide. So this is why you have to be going faster. So if you want to experience more and more and more of your weight at the top, you can't change this number. You cannot change the value that you're going to subtract. That's a fixed value. What you can do is make the centripetal force bigger and bigger and bigger so that you have leftover forces that's what you're going to experience. So imagine me taking this rubber stopper, right? Okay? And so if I'm not going fast enough, the rubber stopper doesn't complete the loop. But if I can calculate that minimum velocity to complete that arc, I wouldn't need the string. But what we're saying, once you get past that point, is that you do need the string, and the faster I go up at the top, the more that's what you're going to experience. So what you should see on number 4, your answers should go somewhere between 16 and about 21. So that should be the range of your velocities on number 4. Roughly about 16 through about 21. And hopefully that makes sense, because the faster you're going, the bigger that centripetal force is going to be, the more force you're going to experience. Let me see. Your answer to number 5 would make a fairly decent GPA. Not bad, but fairly decent. And your answer to number 6 should be something times 10 to the 4th. Okay? All right. Anything else on that? Speak now, or forever hold your peace, or type something in. Or is everybody good? Maddie, are you good? Miss Christmas Tree? Okay. I like the Christmas tree. That's a good look. Okay. All right. So this is going to be the remainder of the time for the next 35 minutes. It's going to be a good news, what we call a good news, bad news day. Okay? So the bad news is I need to go through this whole lecture about Kepler and the history of astronomy and phases of the moon. The good news is that the assignment on Kepler's laws is going to be pretty short. Okay? So it's not going to be horrible. So all we're trying to do today is kind of get you through this basics of Kepler's laws. So you should see on your agenda that today's assignment is going to be this kind of short calculation of Kepler's laws. You should have an assignment. If you don't have the assignment, which I think I've sent out, but if I haven't, email me and I'll send that out. I'll just send it out with today's YouTube video. That way that's going to be simpler. So let's talk about Kepler. So I kind of need to give you a history lesson first. So when you look at the history of science, and there's books that are written on the history of science, and they tend to be fairly boring, I'm just saying. But there is a little bit of intrigue, and this is actually one of the better stories in the history of science. So one of the great debates that happened in all of science was at what type of universe do we live in, okay? So at the time, they thought we were it, okay? That, they saw some stars, and then we knew we had that thing going. But, we were trying to figure out our place in the universe. So if you look at what was called the Aristotelian view by Aristotle, they said, here's the Earth, okay? And this is kind of the ultimate freshman mentality, that everything revolves around us. We are the center of the universe, and everything revolves around us. And it makes sense. If you look at the sun, okay, I'm guessing it's sunny outside, and if you could see the sunrise, you would see this big ball of light appear in the eastern horizon, and you would see it track across, and you would go across like this. So it would be like me holding up this ping pong ball, and me moving it across like this. It's like, oh, okay, I'm stationary, right? The ping pong ball is moving across in front of me. That's basically what you're seeing when you see the sun. You're seeing the sun come up, it sets. You're going to see the same thing on the moon. The moon is going to travel the exact same path. So if you track like a full moon, which is about 2 weeks away, then you would see the moon rise and you would see the moon set. You see the stars, the planets, everything moving around us. And there was like kind of almost like a biblical aspect to it. Because of the fact that, you had, if you go Old Testament, God made man in his likeness and put us on the earth and all this stuff, okay? So, and it made us feel good. It's like, hey, we're at the center of the universe and everything moves around us and it's cool, right? And then, if I drop a golf ball, it falls towards the center of the earth. Okay, so everything appears to be centered around us, and it's this ultimate freshman mentality. So that idea lasted for quite a while, for about 2,000 years. And I'm never going to expect you to know a lot of these names, okay? I'm just kind of giving you the background information. So one of the first people to actually ever come up with like a working model of the solar system based upon the sun being the center. So the earth centered is what we call a geocentric. And again, I'm not going to expect you to remember this. This is just kind of background, okay? So if the earth is the center, that's a geocentric. If the sun is the center, that's going to be heliocentric. Okay? So one of the first ones to come up with this idea was a guy by the name of Nicholas Copernicus. Nicholas Copernicus was a Polish monk, which means he worked for the church. So he is the first one to really write this big scientific paper on the movements of the planets on a sun-centered solar system. But he didn't want to get in trouble with the church because, he was a monk. So he actually did not have his works published until after he had died. He goes, I don't want to deal with this. I've got this beautiful paper, but I don't want to deal with it. So he passes away. The monks published this paper. And this was the first really justifiable explanation of how we could have a sun-centered solar system. Okay, so at this point, this idea was starting to circulate within the scientific community that perhaps the sun is actually the center and we're moving around it. Okay? So, the next big hitter is a guy by the name of Tycho, and again, Brahe. So, let me see if I can find a picture of Tycho. Hold on. There's a good one of him. Okay, you can kind of see it on this one. So, Tycho Brahe was famous for two things. He had a great, like this kind of handlebar mustache, and you can kind of see it here. He had a gold nose. So, again, as the legend has it, Tycho was this kind of bigger-than-life guy. And he was Danish nobility, and supposedly the story is that he got into a sword fight with another person of nobility over how to solve a math problem. They took their math really serious back then. They got into an argument. Swords were drawn, and Tycho got his nose cut off in sword fight. And he didn't want to be seen without a nose, so he had a gold nose furnished and put on. Now, I don't know if he could smell. I don't know how he held it on. I don't know. Okay, that's what everybody asks. I don't know. Never been able to find the answer. So anyway, so he was the first one that kind of had bling. So he had this like gold nose. But from a scientific perspective, Tycho was the first one, and this was done in the 1500s. So this is before the invention of telescopes. So Tycho went out and he built basically his own observatory, and off of an island in the North Sea, because he was Danish nobility and he had money and didn't have a job. So he spent years and years and years and years and years tracking the motions of the planets. So if you look at the word planet itself means wanderer. So if you happen to be up really early this morning, for example, and if you look to the east, it was really cool because you had a very thin crescent moon, you had Mars, and you had Venus. Okay, so you had the moon, Venus, and Mars all there in the night sky. And so the planets move relative to the constellations. So you've got all your constellations like the Big Dipper, Orion, all of these constellations. And the planets tended to drift relative to those constellations. So that's where that word came from. So Tycho Brahe had years and literally decades worth of the best observations that existed on the motions of the planets. Okay, so this is going to be important. Tycho has all the data. Okay? Now, about the same time, there was a German mathematician named Johannes Kepler. Okay? And that's going to be the basis of what we're going to talk about today. Okay? So, Johannes Kepler, it was an odd duck. He was known as the wandering mathematician. And so, what Kepler believed, number one, he had two main beliefs. One, he supported the Copernican idea that the sun is at the center of the solar system, and everything revolves around that. The other thing he believed was that there should be a mathematical way to describe the motions of the planets. Okay? Then that's what he was after. So, in Kepler's mind, he was placed on Earth. He was a religious man. In his mind, he was on a mission from God to calculate and determine the mathematical relationship to describe the motions of the planets. So he viewed this as almost like the universe is like a clockwork, okay? Like there's some mathematical way to describe how these planets move like gears inside a clock. So he heard about Tycho Brahe. So he goes to Tycho and he says, look, I'm on a mission from God, okay? I need your data because Kepler knew he couldn't live long enough to get all of the data and crunch the numbers. So he needed a head start. So as the story goes, and it's a good story. As the story goes, Kepler goes to Tycho and he says, look, I'm on a mission from God. I need your data because this is what I'm trying to find out the motions of the planets. And according to the legend, Tycho says, hey, I like you, you're a little squirrely, but hey, whatever, okay? So, go, when I die, and Tycho was older at this point, he goes, when I die, I'm going to leave you the data. Okay, cool. Kepler's happy, he knows as soon as Tycho, passes away, he's going to get the data. So, as the story goes, Tycho passes away, Kepler shows up to get the data. And the family says, no, I think we're going to hold on to this. It's kind of a family heirloom. He's got, books and books and books of all this data. And we're not going to let you have it. So at this point, Kepler is in a moral quandary, okay? Because he's sitting there going, as Sproles would say, he's going, dude, what am I supposed to do? I'm on a mission from God, but at the same time, the family doesn't want me to have the data. So he has to decide what to do. So this is kind of the first, dark operation in the history of science. So according to the legend, he actually breaks into the castle, steals all the data, and then hightails it back to Germany, where he starts to come up with these laws of planetary motion. So 3 of the great laws that describe the motions of the heavens were derived from stolen data. So it's kind of like this intrigue kind of thing. So, but before we actually get into that, we need to have a brief discussion about Or I want to start with our moon, because you kind of have to understand how our moon works to figure out the observations of the planets. So here's the sun, and here's the Earth. This is not to scale, by the way. And then here's going to be our moon. So A, B, C, or D. So here's the million-dollar question. So this is looking down from on top, okay? So here's the North Pole of the Earth. So here's Santa's workshop right here. Here's the North Pole. So, and here's going to be the moon at these potential locations, A, B, C, or D. And again, this is so not to scale, it's not even funny, but you're going to get the idea. So the first thing that we have to figure out is that when you see the moon in different phases, we need to know where it's located. So here's the question. A, B, C, or D, where is the moon during, where is the location of the moon if it's a full moon? Okay, so that's the first question. So it's A, B, C, or D. Now at this point, if you were in my room, I would have you all go, you know, oh, it would be this lively debate and everything else like this. So we're going to pretend that we're going to have a lively debate. And some of you are going, oh, it's going to be A because here's the sun, and this is what we're going to be looking at. Okay? And some of you are going to say C. Very few of you are going to pick B or D. Okay? Now, but before we answer that, we have to figure out which direction the Earth spins on its axis. So, here's the North Pole, and we all know that the sun rises in the east. So the only way that can happen is that, so here's Al standing on the surface of the Earth. So if the camera is the sun, then as you come around like this and you see like the camera rise, okay, so if, hopefully you all can kind of see this, as Al comes around like this, okay, you can just begin to see him. So what that means is if you look down on top of the Earth is spinning counterclockwise. This is why you look towards the east to see the sun rise, and this is why when you look to the west, you see the sun set. So the Earth is spinning counterclockwise. That's going to be a key part of this story. So to settle this debate, let me give you a hint. On a full moon, this is where the moon is located. Okay, out here. So I'm going to draw that just a little bit bigger. So here's the moon, and there's the dark side of the moon. So you kind of got to visualize this. So this is why I took this ping pong ball, and I've got like the dark side. So imagine that my projector is the sun, and my fist is the Earth, and here's the moon. So the dark side of the moon is facing away from us. So what this means is that here's the Earth, right? We're going to spin around like this, and we're going to see the full moon right here. So on a full moon, the moon is directly opposite the Earth. When the moon is here, okay, and you're like this, there's two reasons why we can't see the moon if it's a new moon. First off, if you look at the Earth and you draw a line across like this, if you're standing here, this would be noon. So this would be noon. So you can't see the moon when it's in this location for two reasons. Number one, you're staring at the sun. That's a small problem. Number two, you're looking at the dark side of the moon. So you can't see the moon if you tried because number one, you're looking at the dark side. Number two, you're looking at the sun. So when the moon is over here though, and you're looking at the lit side of the moon, this is when you're going to get a full moon. So the other thing that you have to figure out is the timing. So for those of you that have actually been out and experienced the world, when you have a full moon is going to rise at sunset, and here's the reason why. So I'm going to draw this bigger. Here's the Earth. Okay? Here's the moon. There's the dark side of the moon. And you have sunlight coming in like this. So, what's going to happen is that if you are right here on the Earth, that's going to be noon. Okay? If you're here on the Earth, that's going to be midnight. And if you're here, because the Earth is spinning this way, this is going to be sunset. And when you're over here, this is going to be sunrise. So, when you have a full moon, and if you honestly, people, if you've never been out and experienced a full moon rise, it's really, really cool. Okay? So in about 2 weeks, we're going to have a full moon. Make a point on your phone to set a reminder and do something. We'll talk about it. But if you've never seen a full moon rise, it's really something to see. So when you have a full moon, then the Earth is going to be spinning in this direction. So you're going to see the sun set in the west, and you're going to see a full moon rise in the east. Now, when you get over here at midnight, the moon is going to be directly overhead, and then when you get here at sunrise, then you're going to be looking in this direction, and the moon is going to be setting, and the sun is going to be rising. So this is why sometimes, like if you drive to school early and you see you see the full moon, and you're going to see it setting in the west because it's on the opposite side of the sun. Now, where we're at right now, and this is why we only get like a sliver of a moon. So right now, the moon is about right here, okay? So when you look at this, and what we're facing is the dark side of the moon. So we're not quite at a new moon, but we're pretty close. So the moon right now is about like this. So this is why we can only see just a tiny sliver of the moon, but we're seeing it at sunrise because the moon is over here. Now, what that means, because Venus and Mars are also visible, so what that means is that here's the Earth, and this is so not to scale again. Here's the sun. So right now, the moon is about here, Venus is about here, and Mars is out here. So when you're seeing the sunrise, you're seeing the moon, Venus, and Mars all kind of in a line. Now, what I'm going to tell you next is going to be an intelligence test that you can use on a date during prom. Okay? And this could go south depending upon how your date answers this question. So one of the things is that if you look at the two interior planets, okay, Venus and Mercury. So they're planets, so here's Mercury's orbit, and here's Venus's orbit. Okay? And here's the Earth. So clearly, if here's the Earth, at midnight, you're over here, and again, this is looking down on top of the solar system. At midnight, you're here. You're facing this way. Mercury and Venus are interior planets. Okay? So if you want to have a relative test of your date's, a relative test of your date's intelligence. Let's say it's midnight, okay? And you're walking out, and you pick a star directly overhead at midnight. And you go, oh, look, there's Venus, okay? There's the planet Venus. And if your date goes, oh, okay, that's kind of cool, okay? And this is where it could go south. So if your date goes, wow, okay, I see it, there's Venus. Your date has no idea of the relative locations of the planets to the Earth. Because at midnight, there's no way you can see Venus because you're looking out this way, and Venus and Mercury are in here. So if your date goes, oh, okay, number one, that your date is global. Now, this is where it could go south. If your date happened to have me for physics, and your date's going to go, you're an idiot. There is no way on God's green earth that's Venus at midnight because we're facing away. So it can make you look like an idiot. So I'm just telling you, if you try that, just a word of caution. Okay? Now, but here's what's going to be important, is that when you look at Mercury and Venus, number one, we can never see, we cannot have like a full Mercury or a full Venus. Because if this is where Mercury and Venus are located, inside the Earth's orbit, we can't see them because, number one, you're looking at the sun, okay, that's a small problem, and you're looking at the shadow side of these planets. So we can't, even if they were here, we can't have a full Mercury or Venus. If they're over here, okay, if they're over here, the sun's in the way, and we can't see them. So the only time that we can see Mercury and Venus is when they're here and here. So this is why Mercury and Venus are known as the morning and evening planets. So right now, we're seeing Venus just before sunrise. So that means that Venus is over here in its orbit. So as the Earth spins around, you're going to see the sun rise, and you're going to see Venus over here. If Venus is in the western sky, right at sunset, that means Venus is over here in its orbit. Because you're spinning this way, you're seeing the sun set, so you're looking in this direction, and you're seeing Venus or Mercury over here. So you cannot ever see a full Mercury or Venus because either you're looking at the dark side or the sun's in the way. So the best that we can ever get, so imagine like this is Venus. So if it's here, so the sunlight's coming this way, this is the dark side of Venus over here, you're looking at this and you can see like this, like half of Venus. So the most that we can ever see of the interior planets is a half of it because we have this big ball of gas in the way, otherwise known as the sun. Okay, so let's talk about Kepler. So Kepler at this point has his data, and that he's stolen from Tycho Brahe, and he's back trying to do these calculations. Now, Kepler, as he put it, waged war on Mars. The reason that he chose Mars is because if here's the sun, and here's the Earth, and here's the orbit of Mars. So, if you look at this, Mars, because it's the closest exterior planet, number one, you have the capacity to have a full Mars. So you can have a full Mars just like you have a full moon, you could have a full Saturn, Jupiter, any of the exterior planets. You have the capacity to see a full lit side, just like you can see a full moon. So, when the Earth is coming around like this, Mars is on this exterior planet. So, Kepler chose Mars because that's the closest exterior planet that he could have a lot of data on. So the only time that you won't be able to see Mars is if here's the sun, here's the Earth, and there's Mars. So the only time that you will not be able to see Mars at all is when it's on the direct opposite side of the sun. So here's the problem. When you're trying to figure out how far away a planet is, it's really tough to do because we can't measure out a tape measure and say, oh, okay, well, you know, if you see Venus, if you see any of the planets, you can see them, but it's really, really tough to try and get an estimate on just how far that is. So, what Kepler did is he got pretty clever. So, here's the sun, and put the Earth here, okay, and here's Mars. Okay? So, at this point, the Earth and Mars and the sun are all in a line. So, what happened, what Kepler had to do, was that Kepler had to figure out where Mars was located. So here's the problem. There's no fixed points in space other than the constellations. So, when Kepler was here on a spinning Earth, okay, he was looking at Mars and he was judging that position. So, imagine this, okay? Sproul sits over here on Tuesdays and Fridays. So I would say, okay, if I'm trying to judge the position of Sproles, so imagine I'm looking at Sproles. Sproles is sitting directly in front of my sink. So I would say, okay, hey, Sproles is in the constellation Sync, okay? Now, Hannah Blair is sitting over here. She's on this side on Mondays and Thursdays. So when I look at Hannah, I see her in front of the door that leads into the chemistry lab. So I would say, okay, Sproles is in the constellation Sync. Hannah Blair is in the constellation Door, okay? Caden is going to be in the constellation Roller Coaster, okay? So I can judge the position of all of you based upon where you are relative to the background stars. So here's the problem. So out here, here's this constellation, some random group of stars. So when Mars gets back to this point right here, that takes about 2 years. It's like 1.88 years. It takes about 2 years to get back to this point. But here's the problem. Mars is going to be back here, but the Earth at that point might be over here. So here's the problem. Even though Mars is back to that same point, if you're here, you're looking at it, and Mars is going to look completely differently because of this view. So it would be like Sproles. If I'm right here, Sproles looks like he's in the constellation Sync. But if I move over here, okay, Sproles now looks like he's in the constellation Fighter Blanket. If I move over here, Hannah looks like she's in the constellation Silver Metal Rack. So what Kepler had to do was he had to compensate for the fact that Mars appeared in different positions. So even though Mars was back there, he had to compensate and go, okay, it's going to appear differently against those background stars. So the computations were really, really tough. So right now it's about 25 after. So if you want to stay on, stay on. I know a lot of you are going to have to go to your second block Zoom meetings. Okay, so I'm going to give you a break. If you need to go to the little boys' room, little girls' room, whatever, okay, go do that. But I'm going to keep talking and recording this, and I'm going to put the rest of this out on YouTube so that you can have this information to get to do that Kepler's laws assignment. So I'm not done. Okay, I'm going to keep going. I'm going to keep recording this lecture. Okay, but look, and I'm going to send that link out as soon as I get it done. So if you need to go, go. I'm going to keep talking to myself, and so I'm going to finish up this Kepler's law lecture. I'm going to put that out. I'm going to send out. You should have that Kepler's assignment, and I'll send that out even if you don't have it. So have a good weekend. I'm going to keep talking, but that's the story. Okay. So, Kepler came up with 3 laws. And no, I'm not going to expect you to know what these laws are. I'm just pointing these out. And these are on your lecture notes, by the way. If you don't have the lecture notes, let me know and I'll send you those lecture notes. I'll just send out the lecture notes even if you have them. That way you have them. So the first law is what's known as the law of ellipses. Okay? So, on the law of ellipses, if you remember from your math class, an ellipse is basically a jacked up circle. Okay? That's all it is. So, here's the sun, and remember an ellipse has 2 different foci. So, the sun is one of the foci, and the other one is some point out in space. So, this created a problem when Kepler produced his law of ellipses, because everybody viewed the circle as the perfect geometric shape. Because they said, okay, look, you know, this is why like wedding rings are circles. It's a perfect geometric shape. All points are equal distance from the center. Oh, it has no beginning. It has no end. Blah, blah, blah. Okay. So the motions of the planets and the stars were viewed as as the realm of the gods. And so everybody thought that since that was the realm of the gods, and the circle was the perfect geometric shape, that's how everything should move, was in circles. So Kepler comes along and says, sorry, Mars especially has an eccentricity to its orbit. It's about 10%. And so that was the beauty of Kepler's data, or excuse me, Tycho Brahe's data, is that he had such good observations that Kepler was able to differentiate and figure out that not only was Mars moving and he was able to estimate the distances, he was also able to figure out the fact that it was changing, that orbit was changing slightly because it was an ellipse. So, why people were upset with that, because an ellipse was kind of viewed as like a jacked up circle. So everybody is going, whoa, whoa, whoa. It's just like God made a mistake. God was trying for a circle, and he ended up with an ellipse. It's like, oh, man, that's heartbreaking. See, and Kepler's attitude is like, look, I don't make the news, I just report it, okay? This is what it is, it's traveling in an ellipse. Now, the second one is more mathematical. And that's the law of equal areas in equal times. Okay? Now this was, for him, this was tough to calculate. So, here's this orbit. Here's the star. And let's say that, like what you're going to do with the lab, let's say that you're going to look at like a 30-day time period. So, here's the star. So to collect this data, number one, Kepler had to figure out the distance to Mars at all these different points. This is why he had to have years and years and years and years of data from Tycho. But imagine this is like part of a circle. So what happens is that here, this area here, in 30 days, so imagine that you're sweeping out a certain area. Then over here, you're also going to sweep out a certain area, also in 30 days. So this area here is equal to this area here. Now, the only way that can happen is if this has a shorter radius, but it has to have like a greater arc length. So what he figured out is that the only way this can work is if you decrease the radius, you increase the velocity. So this is what you have to remember, is that when Mars or any planet is closer, you shrink the radius, but you move faster. When you're out here, you increase the radius, but you decrease the velocity. So what that means is that it's kind of like if you've ever like if you have like a banister like on a staircase in your house, and you run by and you grab that banister and you like slingshot yourself around. That's what happens here. So when Mars is closer to the sun in this part of its orbit, it's going faster. Out here, you have a bigger radius, but you have a smaller arc length, so you're going slower. So what this means is that from here to here, during this region, you're speeding up. But from here to here, then you're going to be slowing down. So Mars spends half of its orbit speeding up, and the other half of that orbit slowing down. So here's what you have to remember. The closer you are, the faster you are. The further you are, the slower that you are. That's the only thing that you have to remember out of Kepler's second law. Now, the third law was the hardest one. So the third law, and this is what he was after, the third law is what's known as the law of harmony. And this is the heart and soul of what Kepler was trying to find. He was trying to find the mathematical relationship for the planets. So, and this is what's actually on your equation sheet. So if you look on your equation sheet, right here below the centripetal acceleration ones, you have TA squared over TB squared equals RA cubed over RB cubed. So this right here, this is Kepler's third law right there. So let me explain what this is. So you have TA squared over TB squared equals RA cubed over RB cubed. So these are going to be the periods. And this is going to be the radius, okay? Now, this is the only time you will ever hear me say this in this class. It is the only time I will ever say this. This is just a ratio, okay? So, if you're Kepler and you're doing this in the late 1500s, you have no calculators, you have no computer programs, you've got nothing. You're doing these calculations by hand. The favorite number that you're going to use is 1, okay? This is just a ratio. So, there's a couple of things that are going to be important about this. This is going to be two objects that listen to me. Here's the most important thing. These two objects have to orbit the same center. So this could be like the period of Earth and the period of Mars. This would be the radius of Earth, the radius of Mars. It could be Mars and Jupiter, okay? You could compare, like for example, we'll talk about the Galilean moons of Jupiter. You could compare this to two Galilean moons of Jupiter because they both orbit Jupiter. But what you could not do is compare the period of our moon to a period of Jupiter's moon. Because our moon obviously orbits the Earth. A Galilean moon is going to orbit Jupiter. So, it doesn't make any difference what these units are. These periods could be in years, it could be in days, doesn't make any difference. This radius could be in kilometers, it could be in anything that you want. All this is a ratio. They just have to be the same. Okay? So, here's what you have to remember out of this. This only works for two objects that orbit the same center. Okay? That's going to be vital. They have to orbit the same center. Now, if you're Kepler and you're doing this, your favorite number is going to be the numeric value of 1. So here's the Sun, here's the Earth, here's Mars. So you have to remember, Kepler didn't know the actual distances. He didn't have a Google. He couldn't say, hey Siri, what's the distance from Earth to the Sun? Didn't have that, okay? So the only thing that he could do is come in here and go, all right, I'm going to let this distance to the Earth be 1 astronomical unit. He didn't know the number. Okay,
the Sun is the star at the center of the solar system. It is a nearly perfect...
My phone I said Siri, and my phone picked up on that, and it just gave me the distances, which is kind of funny. Okay. Anyway, so he let the Sun to Earth distance be 1. Because, number one, he didn't know the actual distance, and this numeric value is the easiest to work with. So, he let this is going to be important on your assignment. He let this have a numeric value of 1. Okay? So then he knew the distance to Mars had to be a multiple of this. Maybe it was 2, 3, 4, something like this. Jupiter farther out, that might be like, 8 astronomical units. So here's what's important. Kepler didn't know the distances. This was all about the ratios. Now, when you're talking about the orbital period of the Earth, Kepler had a choice. He could let the period of the Earth be 365 days, or he could let the period of the Earth be 1 year. Okay, you're Kepler. Wow, I don't have a calculator. I think I will let that have a value of 1, because that's just going to be simpler. So, if you're Kepler, you're going to use a numeric value of 1 all the time. So here's how this plays out. So you're always going to have 4 variables. So let's say you're going to talk about the period of the Earth, and we'll talk about the period of, Mars, all right? And then you're going to have the radius of the Earth, and then you're going to have the radius of Mars. Now, this is where the magic happens. So I'm going to set this up and go the period of the Earth squared over period of Mars squared is going to equal the radius of the Earth cubed and the radius of Mars cubed. Now, this is subtle, but it's important. There's an equal sign here. So whatever value I get here, 0.8, whatever this is, that has to be 0.8 over here. Now, notice these are squareds and these are cubed, okay? So, what I'm going to do is I'm actually going to cross multiply this first, okay? You'll see why in just a second. So, I'm going to take the period of the Earth squared times the radius of Mars cubed is going to equal the period of Mars squared times the radius of the Earth cubed, okay? So all I did was cross multiply to get to this point. What we're going to end up is the functional way of using this equation. So, now, if you're Kepler, oh, I got the period of the Earth. Oh, I'm going to let that be 1 year. So this just becomes 1 squared. It's still there, but it's just 1. Okay, so that just becomes 1. Now, over here, I've got the radius of the Earth. Number one, Kepler didn't actually know the distance to that orbit, but he says, oh, I'm going to let this be 1 as well. Oh, okay. So I'm going to let this have a value of 1. So functionally, what you end up with is the radius of, hold on, is the radius, hold on, I'll get it right eventually. The radius of Mars cubed equals the period of Mars squared. Okay? So, if as soon as you know one of the values, then you can figure out the other one. Say, okay, the period of Mars is about 1.88 years. Okay, so what that means is if I want to find the radius of Mars, then I'm going to take the cubed root of the period of Mars squared. So on your assignment, okay, you're going to have a bunch of these calculations to do. If you can let, and this is a huge if you can let a period and a radius have a value of 1, then it's just the radius cubed is going to equal the period squared. Okay? Now, this only really works if you're in astronomical units, and that's what Kepler was all about, was astronomical units. So, on your assignment, when in doubt, set out all 4 variables. Because on your assignment, a lot of these are going to be dealing with Mercury and the Earth, or Venus, or Jupiter. They're all going to be orbiting the Earth. Or excuse me, they're all going to be orbiting the Sun, so we can use this relationship. But on your assignment, it's just going to be much simpler if you can simplify this to saying, okay, the radius of something cubed is going to equal the period of something squared. So, anyway, there's that. I'm done. Thanks for zooming in. And I'm going to get that YouTube video uploaded, and that Kepler assignment is going to be due on Monday. And then we're going to start this next lab on Kepler's laws, which will happen we'll start that on Monday. So the plan for Monday is to go over this assignment and start that next lab. So anyway, have a good, safe weekend. Avoid people. This thing is getting out of control as far as community spread. So stay home. Wear a mask if you have to go out. All right. See you all on Monday.